Welcome to Finite Element Methods. Today we'll be discussing the 1D finite element formulation for the Timoshenko beam. So let's dive right into it. What are the finite element steps? We need to derive the PDE, the partial differential equation. From there, we need to formulate the general behavior of the element by approximating the solution to the partial differential equation over the subdomain, which we have called element. We need to discretize the structure now into elements, and then we will assemble the stiffness matrix and force vectors, impose the boundary conditions, and finally solve the algebraic system of equations. And once we do that, we can then post-process the results. Timoshenko Beam theory, which we already discussed, so this is a review, in 1921 postulated an approach and formulated an approach to solve beams that are short. And those short beams do require shear flexibility. These theories work very well up to 1/8 typical length. So the thickness to length ratio, 1/8. And here the transverse shear deformation becomes more important. The response is assumed to be independent of the beam section. So that means I can follow the neutral axis and be able to do a good job of understanding the behavior of the 3D structure. The normal in this case, compared to order Bernoulli beam, does not need to be perpendicular to neutral axis during deformation. In this theory, the normal can actually change angles with respect to the neutral axis, and that occurs because this is a short beam. In this case, you see that W is a transverse deflection. Here you see a beam under distributed load Q. And that's very exciting that we can now figure out a way of modeling shorter beams. And if this theory did not exist, you perhaps had to use 3D theory, which would be computationally too expensive. So this Timoshenko beam is very, very valuable here. The displacement assumptions of this theory for planar beam, here again, and I covered this already, but we'll cover it again. The deflection, the actual deflection U in the x-axis depends on just a linear, it only depends on the explicit value of Z through the thickness. So Z is through the thickness coordinate of that beam, and theta is the rotation. W uppercase depends only on W. So that transverse deflection W does not depend on the cross section at all. And also it only depends on the location along the neutral axis in the axial coordinate. Vx of y and z, which is the deflection out of plane, we'll consider that to be zero. But in finite element formulations, the theories are developed so that this is not zero, and you can look at 3D deformations. The kinematic assumption is that plane section remains planar, but shear deformation does occur. And so you have the rotation of the angle of the normal to be theta. You have the slope of the midline, that's W prime. And really the variables of interest when you look at these displacement assumptions is theta and W. Those are the only unknowns in this theory. If I now use the displacement assumptions, I can now come up with the strains that correspond to these deformations, these deflection assumptions. So epsilon xx is the derivative of u respect to x. So that's clearly minus z times theta prime. And then I have the shear strain, which is the derivative of u respect to z. So that gives you theta. You can see that there. Plus the derivative of w respect to x. That's what shear definition is. And you can see here you get w prime now. And so this is what we get for the shear strain. And notice how the shear strain, the transverse shear strain, which is the changing angle between the normal and the neutral axis. Notice how this is non-zero now. Before it used to be zero in order of Bernoulli beam, and that angle will remain at 90 degrees. But in this case, it's non-zero, and that's what we find. We also see here that it depends only on x, and is constant. This transverse shear is constant through the thickness, which is an interesting finding here. The shear angle represents the angle change, And you can see that here in this diagram. The axial strain varies linearly through the thickness. You can see that here, epsilon xx, which is the axial strain, depends linearly through the thickness, like that, z times theta prime. And you can see here it deforms like that. So it went from straight, and now that line element came at an angle. And you can see that here. Um, and that angle is not perpendicular to the neutral axis. So there's that additional rotation. And that's why this is non-zero. I can recover order Bernoulli beam by setting this equal to 0. If I set this equal to 0, I can solve for theta x, which I get W prime, and then plug it back in here, get W double prime. The displacement assumptions that you have here result in these governing equations. In my book, I derive these equations using the total potential energy, and you can actually do that and get to the same results. The finite element formulation can be derived in that manner. So these are the governing equations. Let's look at that carefully. E is the modulus, I is the moment of inertia. Theta, again, we discussed that's the angle of the normal, or the theta. K is a shear correction factor. Typically, the transverse distribution of shear strain is not a constant, is a parabolic distribution, the shear stress, for example. And so K is trying to correct for that, typically 5/6 for a rectangular cross section. G is a shear modulus, A is a cross sectional area, and P is a distributed load that we discussed earlier. W is a transverse deflection, and we already discussed that. So here the new thing is K that you have never seen, but that's a correction factor to account for the fact that in this theory, the transverse shear stress is constant through the thickness, but in real life is parabolic. And so this can be derived to be 5/6 for a rectangular cross section using energy methods, which is beyond the scope of this course. So what I want to solve for here, I have two equations and two unknowns, and the two unknowns are theta and W. And what I want to do is, for example, take this example of a beam that's clamped at one end, loaded in the other end. We want to derive the equations that need to be solved for this cantilever beam. In this case, the boundary conditions are that W at 0 is 0, theta at 0 is 0 because there's no change in angle. And then also you have the location where force is applied, and that's this boundary condition. And then finally, and this should be P, by the way. I apologize for that. At this end, there's no moment applied, so EI theta prime is also 0. If I compare the tip deflection using Timoshenko versus order Bernoulli beam, you'll find that you get this extra term. In order Bernoulli beam, you only get this term, but for short beams, this becomes more become a contributor to the total tip deflection. If I look at the ratio of displacements for a rectangular cross section, this ratio of tip deflection from Timoshenko beam theory to order Bernoulli beam theory shows you that when the thickness to length ratio is small, meaning that this is a very long beam compared to a thickness, this term goes away, and so the Timoshenko beam approximately becomes the order Bernoulli beam theory. But for short beams, you can start to see that that tip deflection becomes important and it needs to be considered. And I covered this already, so this is more of a summary. But note how that tip deflection, that ratio drops to 1 for larger L over T's. And so typically you want to use Timoshenko beam when you have a situation where L over T is 8 or T over L is 1 over 8. 1 over 8 is 1 over 64 when you take 1 over 8 squared. 1 over 64, and you can see here that the error becomes quite small. So how do we derive the equations for Timoshenko theory? We start with the two governing equations. And again, I covered this before, but we're kind of re-deriving things again so you can see how to formulate the finite element from scratch. So what we're going to do is we're going to formulate the residual error. So we take this equation and this equation. Individually, I'll take each equation and multiply by a weight function. Here I multiply by z theta. I've been using V in the class, but it's okay to use different variables as long as you know what you're doing. So the residual function was created for the first equation. The residual is also formulated for the second equation. You can see that here. We're multiplying that by z theta and zw. You can see that there. And then we'll integrate over the domain and equate that to 0. This term right here can be integrated by parts. You can see I put ei theta prime prime on the right hand side and z theta on the left side. And then plus minus transfer the prime over. So now I have a single prime here, a single prime here. And what I've done is I weaken the continuity requirements by integrating by parts. That's what we have done here. On the second equation here, I'm going to take this whole thing, which has a prime and another prime, and I'll put it on the right-hand side. And this ZW will put on the left-hand side. And again, I'll integrate by parts by removing the prime and putting it over here. And I have a plus minus. This bottom one goes to the integral. This bottom one goes to the integral. The cross term becomes a boundary condition. And here I have repeated what's in the previous slide, so nothing to be worried about. And so what you see here is I have this one at the bottom that replaces the top here. And you can see that's what has happened here. And then I have this term that goes here the same way, nothing changes, dx. And then I have this boundary term that came from this cross term, z theta times ei theta prime, evaluated at the boundaries equals 0. And that for that second equation, this bottom term is replacing this whole thing here. You can see that there. And minus px times zw stays there because there's no derivatives. And then I have this boundary term, this cross term, this term gives you this term. And that's a value of the boundary. So what I've accomplished by taking the residual and making it orthogonal to weight functions z theta and zw is that I have been able to then weaken the continuity requirements. And what I can do now is when I select my approximation function, it only needs to satisfy the essential boundary conditions, and the natural boundary conditions are explicitly satisfied or implicitly satisfied in this equation. And the idea, the trick I taught you before, is to look at basically what are the essential boundary conditions. You can see here that when I look at this equation, z theta can be thought of as being theta x. So anything specified theta x is a essential boundary condition. I should multiply by minus 1 to make things nicer. That's what I did there. So I took this equation, multiplied by minus 1, so that dominant term is positive. That's just done as a trick, but there's nothing special about that. That second equation now, I have a zw there. Think of that as w of x. And anything specified in w becomes an essential boundary condition. Notice in order Bernoulli beam theory, w and w prime were the essential boundary conditions. In Timoshenko theory, w and theta are the essential boundary conditions. Anything specified in w and theta are the essential boundary conditions. And notice how w and theta must be continuous across element boundaries. That's how we determine what quantities are the unknowns at every node. We determine that by identifying what are the essential boundary conditions of the problem. And here you can see theta and w have to be continuous across element boundaries, and therefore theta and w are the unknowns at the boundaries of the element. So very exciting stuff. We're making great progress. Now, we're going to substitute some quantities here, and these are basically your natural boundary conditions. So anywhere you see ei theta prime, we're going to put that Q4 there. Q2 for the xi node. So I'm basically looking at node I and j for single element. We also have this one here, which I'm going to call Q3. And then this one here I'll call Q1. Notice how Q4 and Q2 are basically bending moments, and these Q3 and Q1 are shear forces. When I substitute these quantities, which are the natural boundary conditions, into this equation, things simplify a little bit more. So I get this Q4 and Q2 here, and this Q1 and Q3 here. Now, what do I do next? That's a question. So what I'm going to do next is approximate the solution over the domain. What are the things I want to find? I want to find theta and w. So let's find those by approximating solution over the domain. and I will use a linear shape function. We'll use linear interpolation functions for each unknown variable. So I have two unknowns at this node, which I already told you there has to be two, theta 1 and v1, and then here I'll call it theta 2 and v2. These are the unknowns that I need to really track per node. And w of x is approximated as n1 times v1 plus n2 times v2, and theta x is approximated as n1 times theta 1 and n2 as theta 2. These zeros are put in here on purpose so that theta 1 and theta 2 do not contribute to w, and these zeros are put in here so that v1 and v2 do not contribute to theta. You can see here that the shape functions are 1 minus x over L, n2 is x over L, and that, yeah, so these are the shape functions you can derive very quickly for linear interpolation. Notice for order Bernoulli beam, we had cubic interpolation, but for Timoshenko beam theory, linear interpolation can work really well. I'll call this whole thing M bold and this column vector D bold. And again, I'm after W and theta. I'm approximating W and theta using the shape functions, and then these nodal quantities are unknown. That's what we're after here. That's what we're after here. And so now what I'll do, I'll substitute W and theta into the weak form, the first equation, I have that. And notice that for the first equation, I've selected N1 for the weight function, and that becomes 0 node I, j, and then node I becomes 1. For the second equation, I'll then substitute N2 for the weight function, same equation here, and yeah, that's what I've done there, and nothing different there. And now N2 becomes 1 at this node J, but at node I is 0 because of the Kronecker delta property. But you can also check it yourself when it's substituted here and here and here and here for element length L. Equation 3, now I'll shift over to the second weak form. I have that equation here at the bottom. So that's my third equation. And I'll select the weight function to be N1. And then for the fourth equation, I'll select it to be N2. And I plugged in the approximation for W and theta into the weak form that I showed you. I can now take all four equations and put them in a nice matrix that looks like this, with a column vector of unknowns, and the right-hand side becomes this, and then I have these concentrated forces that could occur. If you integrate this using the shape functions corresponding to N1 and N2, you will find that the stiffness matrix is found to be this. So that's done purely in Mathematica or by hand. It doesn't matter. So I can also use, so that is the element formulation. I have completed the element formulation, and now you can use it to solve problems. I'll go ahead and now show you how to derive the theory using the total potential energy. The total potential energy was previously described as this being the integral over the domain volume V, and these are the only non-zero quantities from the strain energy. And then I have this distributed load P that acts on W, therefore you have P times W integrated between Xi and Xj, and then you have these concentrated loads at these ends, which correspond to each of these values. So Q1 goes with V1, Q2 goes with theta 1, Q3 with V2, and Q4 with theta 2, and that's why you see the correspondence here. And that's the work done due to these forces moving through their deflections. We can use the constitutive relationships between for 1D beams, and for the axial stress, we get sigma xx equals E times epsilon xx, and sigma xz equals K times G times twice epsilon xz, where K is that shear correction factor we talked about. Remember, the transverse shear in this theory is constant, in real life is parabolic. This K is trying to correct for that error in the average sense. We can then determine the strains from these displacement assumptions. We know that these are the deflection assumptions in Timoshenko beam theory. We know these are the strengths which I derived earlier. And now what we want to do is plug that into this equation here at the top. Or first plug it into the constitutive law and then plug it into the Timoshenko beam. So when I do that, I'll find that the total potential energy is this equation here. And I invite you to do that. So plug that in here. So plug this in here and this in here. So I did it here for you. So I take that and plug into the constitutive law. And then I take the stresses and plug it in here. And you can see here that that's what I get. I get a lot of square terms. And now this z squared dA gives me the moment of inertia. And then here, this does not depend on dA at all. And that's why this A shows up and everything becomes dx. So you can see this integral has simplified considerably. And this equation here stays the same. Nothing changes there. Now what I can do with this total potential energy, I can rewrite the total potential energy in a more convenient way. And that's very useful for finite elements. What you see here is a little trick. I've taken E bold and called it that. And I put in E bold in a vector, right? And then I have this EI K times GA, and then this also goes here. And what is that doing for me? It's trying to simplify the formulation. But I invite you to multiply this times this times this, and you will see that you will get that same equation here. So nothing fancy. It still works out very beautifully. Again, I invite you to try it, and you will see that multiplication of this times that. So basically, this times that gives you exactly this equation. So very powerful, very important to have it in this manner for a reason. You will see that it's very convenient. Now, I'm going to go ahead and calculate W and theta, and I will use the same shape functions, linear interpolation, and then we get M bold, D bold here. So this is your M bold and this is your D bold. Same thing as we did before. So I have this equation equals this equation. I'll write the TP in a more convenient manner for the finite element formulation. So again, I wrote E bold to be this. Notice how theta prime is N1 prime here and N2 prime there. You can see that there, theta of x is N1 times theta 1 plus N2 times theta 2. So theta prime is N1 prime times theta 1 and N2 prime times theta 2. And you can see I'm getting that. For the second equation, I have theta x plus W prime. And so you can see here that I have this N1 times theta 1 plus N2 times theta 2. And that's why you see this N1 and N2 here. And for W prime, you can see here at the top that W prime is N1 prime times V1 plus N2 prime times V2. You can see that's why you see this N1 prime and N2 prime here. So when you multiply this out times this column vector, you get what this should be in terms of shape functions. And I invite you to try it out. This becomes B bold. This column vector becomes D bold. We do that for convenience. And now I'm ready to substitute E bold into this equation. So I'm going to plug this into this equation. And so then this becomes D bold transpose, B bold transpose, and here I get B bold times D bold. Here I get D bold over here, and N1 and N2 here. Because the only thing showing up is W here in this equation, and that came from here, this row vector here. And then these ones become D bold transpose Q, and recall that to minimize the total potential energy, all we have to redo is remove this D bold transpose and this 1/2. And then if I do that, I come up with the element formulation, which is this equation here. This is exactly what I found with the weak form Galerkin. I can do that, this calculation, I can do that in Mathematica. The shape functions are given to us, N1 and N2. I know what B bold is. I know what the constitutive law is. So all I have to do is calculate B transpose times D times B, I'm sorry. So I'm just calculating this. And notice how D here is that matrix that you see here. And notice how this B here was this B here. The one here at the top. Here, this B bold matrix. So all I'm doing is just programming that into Mathematica and letting Mathematica do the work. I do the element stiffness matrix calculation. Matrix form puts in a nice matrix so you can see the whole thing nicely. And I integrate it from 0 to L. And that's the stiffness matrix I got earlier, by the way. And also, say you have a constant transverse load, then this integration becomes just PL over 2, which makes sense that is PL over 2. I can also go ahead and develop the isoparametric formulation. And what I'm going to do there is take a linear interpolation by using isoparametric formulation. I'll use that to map a domain that goes from 0 to L so that it goes from -1 to 1 for the purposes of using Gaussian integration. And also so I can use the same shape functions for everybody, and the derivatives are the same for every single element. Doesn't matter what length they are. So W now depends on X of C, and theta depends on X of C. And so I have this, and I have this now. The shape functions are now the same for every element. Now we have to compute these derivatives, and that's a little bit tricky now. So I have to then, again, I have to take this derivative here in 1 prime, for example. Well, I can't quite do that because n depends on C now. So I have to find a way of doing that. So you can use chain rule, as shown here, solve for this one, which I've done here, using the Jacobian. I already went through this. That's why I'm going faster. But X of C is this right here. And then J equals partial of X with respect to C, which is necessary for calculating this ratio here. And that's L over 2. And yeah, so I solve for this. And now I can plug this into this equation. I also have to take this derivative here with respect to n2 and then repeat the process. Solve for this because I need to substitute that here. Now, these derivatives are very easy to find because n2 and n1 is this and n2 is this. These ones depend on C. So these derivatives now are easy to take. And so I can plug those things here. So let's see, for theta prime, I have substituted that there. I have substituted that there, and this one here, and this one here. These one don't have derivatives, so they stay alone. They only depend on C, so that's easy. So now we can evaluate all these derivatives, and we get this equation here. This is your B ball now. And notice how dx can be substituted by L over 2 deep C. And B ball remembers this here, which is the same for every element. The integration goes -1 to 1. The distributive force also goes from -1 to 1, with dx being substituted by L over 2 deep C, the Jacobian times deep C. And these calculations can be performed in Mathematica very easily. So you can see that here n1 is 1 minus C divided by 2, and n2 is 1 plus C divided by 2. And then the B ball matrix provided here. I have the constitutive law. And when you integrate from -1 to 1, you get the same answer I got before. Everything is the same. So this demonstrates that your parametric formulation worked really well. In my book, I have a numerical example that walks you through Timoshenko Beam theory and with numbers. So I invite you to check out that chapter. I could integrate this B bold. So B bold, all this stuff has to be integrated numerically, typically. You can use a 2 quadrature rule, and it will be very successful at integrating this really well. And the reason 2-point quadrature should be used is because B bold has 1 amount of C, and so when you multiply everything out, you will have polynomials of second order. So you will have a quadratic polynomial, and so a 2-point quadrature rule is appropriate level that you need for integrating these exactly. But there's a problem. And let me discuss a fundamental problem with the way we've done it. And it needs to be discussed because this occurs a lot. When I use a 2-point integration, Gauss quadrature point, because we already discussed that a 2-point quadrature rule is correct for integrating a quadratic polynomial. But there's a problem. A 2-point Gauss quadrature rule is really evaluating V1 and V2. So this is my domain minus 1 to 1. And you can see here that it's constant at this point and this point for V1 and V2 because V1 and V2 are the deflections. And theta 1 and theta 2, there's also a variation there. And you can see I'm going to evaluate in Gauss quadrature rule right about this point, somewhere there and there, if you recall. And so you're sampling here and sampling here, sampling here and sampling here. Okay? So this is what you got. That's the situation you have at hand. So the Timoshenko beam element with 2 points converges to the exact solution for thick beams, but it doesn't do a good job for thin beams. So you can see here, even if you want to increase the number of elements, and I compare the finite element solution to the exact solution for thick beam, for very thick beam, the solution gets to the exact solution really quickly. But when I take a very thin beam, the Timoshenko theory falls apart and is almost so far apart from the exact solution. That ratio is so off. Like a ratio of 1 is the exact solution. A ratio of 0 is basically horrible. Like it's so off. You can see that the Timoshenko beam theory is acting very stiff, extremely stiff. And it's not moving. Like I'm applying this load and it's hardly moving. You can see the deflection there is almost 0. And the exact solution is the correct one, of course. But here, when you have a thick beam, it does a very good job. When I go to 8 elements, I'm getting a great approximation compared to the exact solution. And you will want to have Timoshenko also work for long beams. So it would be nice to have a formulation that works for short and long beams. And clearly this is not working out. But I want to bring you back to this image. We're sampling at this point and sampling at this point. I want to come back to that. So let's look at why that is happening. Why is this happening? So let's look at the pi. Pi is this equation here, which is total potential energy. If I divide the whole thing by EI, I get this expression. And notice how KGA divided by EI for rectangular square, rectangular cross section, where gives you G times BH, which is the width and the height of the cross section. I is 1 over 12 BH cubed, so that's why you see this 12 here. And when I work everything out, I get 12 kg divided by EH squared. Notice that when H becomes really small, uh, which means I have a thin beam, this ratio blows up basically. So as H becomes thin, this ratio blows up. And unfortunately, that's what's multiplying this here. The only way that pi cannot blow up if this coefficient was 0. And that's kind of causing some issues. And let's see what those issues are. I'll show you in a second. So this, as H goes to 0, because that's what you have for thin beam, the thickness, H, the only way that pi does not blow up if this coefficient here goes to 0. That's the only way. So let's see what's going on. So what is this quantity here? This quantity here is shear. So let's look at shear strain. So shear strain is theta minus W prime, which is exactly what you see here. But let's look at what W prime is. W prime is V2 minus V1 divided by L. And I invite you to check that out. That came from Wx equals N1 times V1 plus N2 times V2, and N1 and N2 are the shape functions. So that's where this came from. Theta here is this expression here. But this is a constant, and this is a linear function, and somehow this has to be equal to 0. So because it is constant, and this is a linear function, you don't have a way of dealing with this. So you can see here that V1 and V2 I'm not able to, when I'm sampling here and here, I'm not able to get anything else. I'm getting a value here. It's forcing me to it's forcing me to a value. And so how are you going to make something that's constant the negative of this linear function to get zero? I mean, that's very hard to do. Um, we want the fact that as the beam becomes thinner and thinner and thinner, behaves like order Bernoulli beam. That's my dream. It's not happening with these shape functions. The const for W prime, I have a situation where this is constant, theta is here, and I don't know how to get that to zero. The derivative of the deflection is piecewise constant, which is this, and should coincide somehow to this value here that's piecewise linear. And so that enforces both variables to be global constants, meaning I get zero here and zero here, basically. In other words, I'm getting no deflection because V1 and V2 represent the deflections. And that's why you see that for thin beams, it's not deflecting because it's forcing V1 to V2 to be zeros. So that is what is going on here. I repeated the plot here again to kind of show you what's going on. V1 and V2 are stuck as close to zero. And this is from a book called Taylor, ZNT. And you can see here that W over W order Bernoulli beam um, does fairly well. But as the beam becomes thinner, things start to fall apart. The deflections in Timoshenko are almost zero, and I'm not doing really well here. So the main issue is that the deflection rotations of cross section do not have compatible interpolation. And so therefore it's not possible to produce a transverse shear strain to be zero. It's not possible to cause this to be zero for thin beams. For thin beams, this has to be zero. But I can't get there if W prime is a constant. I have no way of making this happen. So the beam becomes very, very stiff. And you can see here that that's what's happening with these dashed lines. And that's a 2-point interpolation. You can see that here. But if I reduce the number of integration points to 1, something very miraculous happened. And that's that get a really close solution to beam theory. Timoshenko approaches the order Bernoulli beam theory really well, which is very strange because I told you earlier I need a 2-point integration scheme to get there. Okay. And I 2-point integration was needed because I have a quadratic equation, but polynomial. But I'm showing you how 2-point here in this case did not work out, and 1-point integration did a better job, although it's less accurate integrating. Why is that? It's because I'm now sampling somewhere in between here, and so I'm able to then get there. So the following approaches have been used in the past to achieve a better solution. And this is called shear locking. This issue is called shear locking because it's locking the solution. It's not letting it bend. You can use a higher order interpolation. That's one solution. And I show you in my book how to do that. You can use reduced integration. So those are two approaches that exist. 2-point Gauss quadrature was required to exactly integrate an integrand that has a quadratic polynomial. But if we use a 1-point integration, we're sampling the rotation 1 point. And so that allows us to make the rotation constant, and that makes it the same order interpolation as W. So going back here, I'm now sampling only at 1 point with 1-point integration. So now I'm able to then get these two to add up to zero somehow, which I couldn't do before because they're vastly different orders of polynomials. Here, you can see that here. This is constant and this is a linear function in the shear calculation. And so, but now that I'm sampling only at 1 point at zero, C of zero, I can do that. I can get there. And you can see here how the 1-point Gauss thin beam does really well when I go to 8 elements. Actually gives me the same, after 2 elements, even 1 element gives me almost the same answer. So for 1-point Gauss thick beam, 1-point Gauss thin beam, really nice. I can get there. So the limitation of Timoshenko beam finite elements is that if the displacement and rotations are interpolated with the same shape functions, there's a tendency for the element to shear lock, and it exhibits a very stiff structure. Reduced integration is not an engineering approach, but it overcomes the issue with shear locking. Note that these issues occurred when we have completeness and convergence properties. There are two solutions that can be used. One is called the consistent interpolation, and the other one, and what that means is I will use a quadratic approximation for the transverse deflection and linear approximation for rotation. Why that works? Because if I do that, then W prime becomes W prime is W is quadratic, so W prime becomes linear, and now they have a linear function here and a linear function here. I can add them up and figure out a way of getting to zero if I needed to for a thin beam. Well, this was locking me. This is constant. This is a linear function. If I needed to get to zero, I couldn't do that for thin beams, and it was stiffening up all uh, the behavior of the structure. Superconvergent element uses a cubic polynomial for transverse deflection and quadratic polynomial for the rotation. This produces the exact solution for Timoshenko theory in some cases. The Timoshenko beam theory, which is called shear flexible beams in abaqus, these from the abaqus manual, you can see they have those. It's called Timoshenko beams, and they come into several forms, B21 and so forth. It allows for transverse shear deformation, and you can see that the manual is consistent to everything I'm teaching, 1/8 there. And everything here is very similar to what I discussed. It allows you to look at different shear correction factors. You can see here, for a rectangular cross section, you get 5/6, which is what I discussed, and that's consistent with abaqus. For other types of geometries, the shear correction factor could be different. You can see here the implementation abaqus. For Timoshenko beam, I'm using the two-noded element, B21, and all I've done is just basically provide a fixed boundary condition here and here, and apply a load of 9,000 pounds. But everything else is the same. The only thing I did was to change the element type. In the previous 2 lectures ago, I covered order Bernoulli beam, and I showed you what the input deck looks like. But for Timoshenko, all we have to do is change the element type here to get it to work. But very exciting. Timoshenko works for thick beams, also for thin beams if you were to use a reduced interpolation, reduced integration. But Timoshenko works for short and long beams, while order Bernoulli beam only works for long beams, but does not work for short beams because it's not formulated in that manner. With that said, thank you so much for listening to this lecture, and I hope you enjoy it. Have a great rest of your day.